So today's lesson is all about problem solving with quadratic relations. Okay, now the goal is this. I can use Desmos to interpret the graph, and what we're often looking for is a vertex, a y-intercept, maybe the x-intercepts that we were talking about before, and the possible point on the line, point on the graph. Now remember, a parabola looks like this, and often the parabolas that we have will look something like this. They cross the x-axis at a certain point, and they also have this thing here, the point of the y-intercept, which is of the point 0y. And then we also have our x-intercepts. Let's call this x1, 0, and our other point x2, 0. Now, our graphs will look something like this a lot of the time. Sometimes the graphs open down, but when they do open down, all that means is we just have a graph that looks like this. So the graph might look something like this. It goes on forever, where we have our x-intercepts here and here, and our y-intercepts, 0y, somewhere down here. Now we can use that to help us find information like the maximal point, which happens at our vertex. Remember, our vertex is either the lowest point or the highest point on our problem. And that's pretty much it. So here's our first example. So imagine that we have a plane. I spelled plane wrong. A plane used to simulate the weightlessness of flying by flying in a parabolic path. So basically what it does is the plane, as it flies, it drops and then goes back up. That's all it's doing. Okay. Now, the flight is modeled by this. By h is equal to negative 10t squared plus 300 t plus 9750. So this is what we call the objective function, and we are going to use this in. Now let's just cordon off this bit of the note so that we don't mix it up with anything else. And what we're going to do is we're going to take all this information that we have here, and we're going to make sure that we answer a few questions. All right. Now, h is equal to all of that stuff, right? And I'm going to explain what all the variables mean, where h is equal to the height, and t is equal to the time in seconds. Now, here's what we need to find. So these are the things we need to find. We need to find the maximum height of the aircraft when it's at its maximum height, the altitude when the weightlessness happens, and when is it reached, and if the aircraft loses its weightlessness at the same altitude as it's achieved, and how long does it happen? Now, let's go over to Desmos and take a look at the graph and see what's going on. To type in that equation, you're going to have to write h is equal to negative t Shift 6, so that gives us our caret sign, so that's this thing here. 2 plus 300t plus 9750. So all we're doing is we're just copying down our graph. So we write, goodness, it's off the charts. So what we're going to have to do is we're going to have to readjust our screen. So I'm like shrinking the width left and right, and then shrinking it up and down, and then pulling it in and out. You can use that on your phone. Now, if you're having issues, you can always go and change the width of what we see on the screen by actually clicking on the x-axis. This is the start value. This is the big N value for our x values, and then this is our minimum value for y and our maximum value for y. So now that we've done that, every time we do these, we always had to calculate. We always needed to know what our vertex was. So just double tap where the vertex is, double tap where the y-intercept is, and if you're smart, you make sure that you also double tap where your zeros are, your x-intercepts are, so that we can have this and actually look at it, because all of these points will give us bits of information that we need for our problem. So with our basic graph, we have h is equal to negative 10t squared plus 300t is 970. Now, remember, I said that we were looking for the maximum point, i.e. the highest point on our curve when we were looking for its maximum height. And that occurs on this portion of the graph. And this is why we're using Desmos, so we can visualize what's happening. Now, in this case, the first value represents time, and the second value here represents the height. And it's always that way. Anything that is x, that is our x, always represents the first value of our information. And that's all it is, right? So what we've just done here is we've identified a couple of key points. We identified its height, and we also identified the graph's time it took to get to that height. So let's go and answer some questions. So now here's what they asked for in our problem set today. They asked us for the maximum height of the aircraft and when is it at that maximum height. Now, we literally took that information and so we need to remember that the x portion of this is the time, and this portion here of our vertex is the 12,000, which is just the height. Now, so if we were answering our problem today, we would say that we're actually, first of all, we have to get this from the vertex all the time. So anytime we're looking for a max or a min, so we get that from our vertex when looking for a max and a min. So when we do that, that gives us some information. So now let's go and answer that based on what we know. So for A and B, we were looking for the maximum height. So we would say the maximum height was 12,000 meters. Now, the time is not actually measured in minutes, it's actually measured in seconds. So this happens at 15 seconds. So now let's go over to our base sheet and we'll make sure that we summarize it. So now, remember, we said that the maximum height of the aircraft was 12,000 meters, and it came from the wide portion of our vertex, right? And that's what we're going to say is our maximum height, which is 12,000, right? Then when is it at its max? So when it's at its max comes from the time at which it has its vertex. So it ends up being 15 seconds. And now let's go and try to figure out when the weightlessness actually is reached. Now, here's how I know what our graph looks like. When we look at our graph, remember we said we had our time and we had our height, okay? And we use that to help us figure out what the time was and when our vertex is, right? For our vertex. So let's go and get rid of all this stuff and go back to our problem again and see if we can figure out when our weightlessness starts, right? Now, I want you to think about it. Is it possible for us to go back in time? Well, any betting man would realize that that is not the case. You can't go back in time. Now, that means that everything in this graph from this side on is not good. You can't use it, right? But we do know that at this time right here, our time is equal to 0 seconds, right? Now, notice it's actually touching our y-axis, right? Wait a second, and this is our x-axis. So hold on a second. Isn't this just our y-intercept? Right. Now, this means that the following happens. Weightlessness starts here. Starts at t equals 0. Okay, so the plane is flying and now it's actually weightless from here all the way to, I don't know, maybe here or maybe down here, but we'll figure it out. But it actually starts its weightlessness right where our green marker is, right? So its weightlessness starts at time 0, which means that we also know its height. And in this case, its height is 9,750. And let's go on to our next problem. So now let's get back to our problem. Let's talk about it. So right now, we're actually taking a look at this part, the altitude at when the weightlessness was reached. Remember that we said that everything on this side of our chart was useless, but the point where it starts is where our y-intercept was. So this was just our y-intercept, wasn't it? So let's write that. So in essence, we have our time equaling 0, but our height being 9,750, which was our y-intercept, right? So the altitude when the weightlessness is reached is 9,750 meters. There it is. So the next question that we have to deal with is this part here. If the aircraft loses weightlessness at the same altitude as it's achieved, how long does that happen? So what we're going to have to do is we're going to have to go back to our graph and we're going to have to see where the altitude is exactly the same on our graph and then use that to find that extra point and then use that to figure out the distance or time it takes for the weightlessness to occur. So just a quick recap. So remember what we did was we literally walked ourselves across the parabola to this point here. We knew that was 0,975, but then we read off the graph that this was 30,950, which means that we actually traveled from 0 to 30 seconds on here, which meant the following. The aircraft has weightlessness for approximately 30 minus 0, which equals 30 seconds. You notice how I always had to subtract, take my left side, subtract from my right? That will be used later on when you have length calculations to do. Okay, now your problems are all based on these type of calculations, whether it be height or time or other things. So what I want you to do now is I want you to practice what we have just done on these other questions that I've given you. Okay, so there's a bunch of questions, and what these questions allow me to see is if you can actually identify the vertex, the starting, the y-intercept, or any x-intercepts that allow us to figure out some answers. Okay, now get to work. Questions are posted online. So here we have our graph, right? And remember, a long time ago, we took a look at this thing called the axis of symmetry, right? You know that the distance from, say, here to here is the same as the distance from here to here, isn't it? Which means that our matching height is going to be right here on our parabola. And remember that that point there was 0.9750 for our starting height and time, right? So that means this value here, where it has the same height, happens at 30 seconds, and its height is 9750. So it actually travels from 0 to 30 seconds, which means our total time is 30 seconds for our flight to have weightlessness. So let's quickly do a quick summary of what we just looked at. So for word problems in today's unit, what you're going to be doing is you're going to be using Desmos to identify the vertex, the y-intercept, the x-intercepts, and that's about it. Now, each of these things that we have here in our parabola, remember, a parabola, if it looks like this, will either look like this, where we have our x-intercepts here, and then we have our y-intercepts here, and then we have our vertex v here. And each of these, when you refer to them, will be in point form. Okay? Now, every question that I pose to you in today's lesson will have something to do with either the vertex, the y-intercept, or the distance between these 2 points, or the distance from here, from x equals 0 all the way out to the rightmost intercept, right? That is what we're doing today, okay? So if you haven't done so, make sure that you've done the practice for lesson 1, because lesson 1 will allow you to do everything here, because you're going to be able to identify the vertex, the y-intercept, the 2 x-intercepts, if there are any, for every problem that I give you, okay? All right, so now get to work, please.